Hello, Professor Halsey here, and this is Module 4, Circular Motion. Okay, so here we're looking at conversions between degrees and radians, radians and revolutions, and RPMs to radians per second, or rotations per minute to radians per second. Okay, so for A, 45 degrees is equal to 45 degrees times pi radians divided by 180. Now, let's look at that on the calculator. Okay, so this calculator has a pi function, so I'll use that and divide that by 180. And then I'm going to multiply that by 45. And that gives me 78.785 radians. Okay, so with each of these, we're really just setting up a ratio to find out what percentage this is of the total ratio. So here we have 13 radians to 1 revolution per 2 pi radians, which is a full circle, or 1 revolution. All right, so I'll take the 1 divided by 2 times pi. And then I multiply that by the 13. And I get 2.07 because I'll round it to 3 significant figures. Okay, again, we're setting up a ratio here. We need to convert revolutions per minute to radians per second. So we need a conversion for the revolutions and for the minutes. So to convert minutes to seconds, it's 1 minute is 60 seconds. For the revolution, 2 pi radians is 1 revolution. So now we're going to take 70.5 times 1 divided by 60 times 2 times pi, and we get 7.38. Again, we're going to 3 significant figures. Okay, here a centrifuge in a medical laboratory rotates at an angular speed of 3,400 revolutions per minute. When it's switched off, it rotates through 48 revolutions before coming to rest, or 0. Find the constant angular acceleration in radians per second squared of the centrifuge. Okay, so if we look at the formula they're giving us, it's actually similar to what we were using last week with the 1/2 mv squared, and you may think I'm crazy, but here you're using the angular momentum or the angular velocity, so this would be our final velocity squared minus the initial velocity squared divided by 2 times the change in the distance, only the distance here now is angular. All right, so I'm a little, it's a stretch, but this is really similar. If you look at it in terms of what we did last week and what we're doing this week, then the formulas are very similar. All right, so to find the initial angular momentum, we look for, or we're converting our 3,400 revolutions per minute to radians per second. And we looked at how to do that up there using 1 minute per 60 seconds and 2 pi radians per revolution. So once we multiply this all out, we end up with 356 radians per second. And we know the centrifuge goes through 48 revolutions before it stops, so we can convert that to radians. That's 302 radians. Again, using the conversion that we used in number 1. Now we can use this formula up here and solve for the angular acceleration, because our final angular value is 0 because it comes to rest. So we have 0 minus the 356 squared. That's the WI squared there, 356, divided by 2 times 302, which is the radians, or the distance that it went, times 2. I don't know if I said that part. All right, so we come out with negative 210 radians per second. And 3 significant figures on these in the division. Okay, here the diameter of the main rotor and the tail rotor of a small engine helicopter are 7.5 meters and 1.01 meters respectively. Their respective rotational speeds are 441 revolutions per minute and 4,150 revolutions per minute. Calculate the speeds of the tips of both rotors. Now, if you've never seen a helicopter, it's got a set of big blades on top that controls the up and down movement, and then in the back end of the helicopter there's a smaller tail rotor that moves the horizontal left and right. Okay, so, well, I guess all around, but you gotta look at it from the joystick perspective, so it does kind of move all around. So for the main rotor, the velocity is calculated by the radius times the speed that it's traveling at, and then we use our conversions to go from revolutions per minute to radians per second, and multiply that times the distance, which was half of what is given, because it's the radius, not the diameter. So we need half of the diameter. All right, and then for the tail rotor, again, it's half of the diameter times its speed in revolutions per minute converted to radians per second using the conversion here. And what I tend to do is store a constant for this number, since you use it so many times. If you store this number as a constant, then you just pull it up and multiply it times whatever you need to multiply it by. Compare the speeds with the speed of sound, which is 343 meters per second. Okay, so if the main rotor is going 173 meters per second and the velocity of sound is 343 meters per second, then we're going at right at half the speed of sound here. Then the tail rotor at 219 meters per second is going just over half the speed of sound. It's been suggested that rotating cylinders about 20 meters long and 4.5 meters in diameter be placed in space, used as colonies. What angular speed must such a cylinder have so that the centripetal acceleration at its surface equals the free fall acceleration on Earth? This is one of those really good questions. If you were up there, you'd want to make sure somebody had calculated it, I guarantee you that. So if we look at the radius of the cylinder, and it's, I guess it's miles long. Okay, so we're converting miles to meters here. Then from the acceleration equals the radius times the angular velocity squared. The required angular velocity is, and we take the square root of 9.8 meters per second squared. 9.8 divided by the 3.62 times 10 to the third we found up here. And take the square root of that. I don't know if I said that right. 9.8 divided by this, and then we take the square root of that, and that gives us our radians per second. And then to enter that for our answer, we take this and move the decimal point 2 places, so it's 0.052. Human centrifuges are used to train military pilots and astronauts in preparation for high-G maneuvers. A trained fit person wearing a G suit can withstand accelerations up to about 9G, which is 88.2 meters per second squared, without losing consciousness. If a human centrifuge has a radius of 3.79 meters, what angular speed in radians per second result in a centrifugal acceleration of 9 Gs? All right, so to find that, we have our accelerations, the velocity divided by the radius, which is the formula we've been using, the radius times the angular velocity squared. Okay, so to solve for the angular velocity, we take the square root, and this is just like the last problem. Our acceleration, we want to be 9 Gs. Our radius was given at 3.9. It was given as the radius, so we can use that number. So 9 divided by 3.79, take the square root of that, and we have 4.82 radians per second. What linear speed would a person in the centrifuge have at this acceleration? Okay, so to find the velocity, we take the radius times the angular speed, and we have the 3.79 times the 4.82 radians per second, and they would be going 18.3 meters per second. Okay, for number 6, you need to watch the little vignette, and that will help you answer these questions, hopefully. In our next one, a heavy turntable used for rotating large objects is a solid cylindrical wheel that can rotate about its central axle with negligible friction. Think of like a big, one of those things that move equipment, big heavy arms, robot arm. The radius of the wheel is 0.33 meters. A constant tangential force of 300 newtons applied to its edge causes the wheel to have an angular acceleration of 0.836 radians per second squared. What is the moment of inertia of the wheel in kilograms meters squared? Okay, so we can use the net tangential force to find the momentum and the angular velocity. And based on that, that means we can find the momentum because we were given the tangential net force of 300 newtons. And the radius, well, then we're going to use that. Going to use the radius and the force and the sine of the angle to actually find that net force. So we have the radius times the force, and the sine of 90 degrees is, go figure it out, and you'll see why it's not in here. And the angular momentum that was given, or the angular acceleration, 0.836. So 0.330 times 300 divided by 0.836. What's the mass in kilograms of the wheel? For a solid cylinder, the momentum equals the mass we just calculated times the radius squared divided by 2. Then we'll convert that to solve for the mass of the cylinder. 2 times the momentum divided by the radius squared. So we have 2 times the 118 kilograms per meter squared that we just solved. And the 0.330 radius that was given. And that would be, you move your decimal, since this is positive 3, you'd move the decimal point 1, 2, 3 places, and that would be 2170. The wheel starts from rest and the tangential force remains constant over a time period of 4.5 seconds. What is the angular speed in radians per second of the wheel at the end of the time period? All right, so the angular momentum equals the final angular momentum plus the speed times the time. All right, so the final was 0 plus, and here we have the speed that was given at 0.836 radians per second squared times the time that was given of 4.5 seconds, and that gives us the 3.76 radians per second. A mechanic changing a spark plug in a car notes that the instruction manual calls for a torque with a magnitude of 10 Newton meters. If the mechanic grasps the wrench as shown in the figure below, determine the magnitude in newtons of the force she must exert on the wrench. She got some manly looking hands. Notice that the point about which the torque needs to be applied is the center of the spark plug. The basic definition of torque is the radius times the force times the sine of the angle, where r is the magnitude of the vector that locates the point of application of the force relative to the point about which we are taking the torque. And that's what they're looking at here. Force is the magnitude of the applied force, or F is the magnitude of the applied force, and theta is the angle between the direction of the two vectors R and F. Okay, so our R is this way. So we transpose that down to here, and this is R and F. Knowing the magnitude of the required torque, the point of application of the force, and the angle between the direction of the vectors, we can determine the magnitude of the force. It's going to be the torque with the magnitude of 10 Newton meters that's required. The radius was given at 0.3 meters. And the angle, we take the sine of 60 degrees. Okay, so we have 0.3 meters times the sine of 60 degrees. Take that, and then 10 divided by that answer gives me 38.5 newtons. Okay, hope that helped with Module 4. If you have any questions, please let me know. Thank you.